to the second day of the macOS and iOS security internals advent calendar. Today we will have a look at Mach-O binaries, because as a security researcher, this is the kind of binaries you will always have to deal with the moment you touch any kind of executable code in Apple devices. Mach-O binary is short for Mach object binary, and it basically used for storing any kind of executable object inside macOS and iOS. So these are libraries, these are bundles, these are drivers like kernel extension or driver kit extensions, but also the kernel itself is basically a Mach-O binary. These files were officially documented by Apple in some nice document. This document also contained a number of images about the structure, and these images I have also used inside this slide deck. However, the document disappeared from the public web. It said that it moved into some deprecated documentation, but even inside there the document doesn't seem to be containing the images anymore, so I cannot put a link to the original document here. So macOS has a command line util called utils, which will allow you to look at the structure of Mach-O files directly from a command line. We will have a look at this later on. So to understand Mach-O files, it's quite handy to see a Mach-O file as three major regions. So first you have a header region that is a very short fixed size header that contains just the basic information about the file. Then you have a region called the load comments, and this is basically a dynamic length area that specifies more about the structure of the file and information that's required for loading a file. And then you have the biggest area, which is the data area, which contains all the information that does not fit into the other two. For example, the content of segments, like code signing information, and all of the stuff that is quite large. So let's start with the header. We ignore here that there is a legacy 32-bit header, because nowadays we are only interested in 64-bit files. So as you can see here, we have a 64-bit header that starts with the magic that identifies the file, and then it specifies the CPU type and the subtype. So nowadays it's likely ARM and an ARM 64-bit ABI, but it could be also x86 and so on. So then this header also specifies what kind of file it is. So if it's a library, if it's a bundle, if it's the main binary, if it's the kernel, if it's a kernel extension, and so on. All of this is basically stored in the file type. There's also the possibility for adding some flags, like something like this is like a position independent binary and stuff like this. So, but aside from that, the most important information inside this header is like the information about how many load comments will actually follow this header and how big they are in total. Because the load comments are the ones that are actually having all the juicy information. Yes, so load comments are variable size, and that's why they all start with the same kind of short header, which is the comment followed by the comment size. The good thing about this is that also tools can just implement a subset of load comments that they are interested in, and they don't need to know anything about the structure of the other load comments, because they can always skip them by jumping over the size that is specified in the size. There's like a new convention for a while that if the highest bit in the comment is set, it's considered a required load comment. That means the dynamic linker will error out if it doesn't understand the specific load comment. Like for example, if there's a new binary from a newer version and you try to run it on an older macOS, then this can happen, that there's a new type of load command that's considered required, and the dynamic linker will error out if it doesn't know that. Yeah. So the next thing is that let's have a look at some of the load commands that exist. Some of them, for example, will specify the initial layout of the file in memory, which basically means, oh, we have these kind of segments, they are separated into certain sections, and so on. It also specifies where is in the file the symbol table, if there is one, or where is the main thread, where is the entry point, where are potential executions happening inside the file. Then it specifies what libraries are we importing, so what libraries are required for binding the imported functions. Then more and more binaries are these days code signed, so there's also load command specifying where is the code signing information inside the file. And especially for iOS, there's the possibility to have DRM protection of the code inside a file. So there's a load command that tells us, oh, there is actually DRM protection inside this file. And then we have the data area, the data region at the usually towards the end of the file, and that's also variable size. It's quite large usually, and it contains all the information that cannot fit into the load comments. For example, the actual content of segments and sections, or the actual symbol table. Then you have other link edit information, like where is the rebasing information, the binding information, where is the export tree, and so on. And of course, for code signed files, the code signing information must be stored somewhere, so it's also in that region. And there can also be additional optional debugging information, like where do the functions start as a table of that, or where are data encode areas and stuff like that. That's all inside the data area. Let's have a look at the header files from the SDK. So first we find out where is the SDK in the file system. So it's basically here, and then we can run more on user include Mach-O, and then the most important header file is loader.h. So we can look into this, and we can see here now Mach loader information. So it's see here the definition of the Mach header. This is the traditional 32-bit one. We have the 64-bit one. Then we have all the flags. Then we have the definition of how does a load comment looks like. And then we have all the load comments. Then for each load comment type, we have the top possible data structure. That this was just the segment flags that can exist. Here we have section definition. Now we have the section types and attributes. They're defined here, and so on and so on and so on. And all of this is in the loader.h file. Let's have a look into how util works on the command line. So when we run util-h, we can see there's a bunch of command line parameters to this. Most of them are too much for now. We just want to have something like the header. So we have the h and the load comments. So let's have a look at util-h on, let's for example bin ls. We see this information here, we see the magic, we see the subtype, the CPU type, the subtype, the capabilities, the file type, the number of load comments, the size of the load comments, and the flags. We can also use V to see this decoded. Yeah. Once we have that, we can have a look into the load comments. So we use -LV, and we can see here now, okay, we have the first load comment, which is a segment, it's a page 0 segment. Then we have the segment, which is a text segment. Then we have the section, so there's an __ text section. We have an __ stop section, const, C string, unwind info, and then we have another segment which is __ data const. Inside that we have an auth_God section, we have an _God section, we have a const section, and then we have the __ data segment, an __ data section inside the segment, a common, a BSS, yeah. Then we have a link edit segment. Then we have our DILT info only information here. We have a symbol table, dynamic symbol table. We have the definition of what is the dynamic linker. We have the UUID of the file. We have information about where was this built, macOS with specific minimum version and SDK version. We have a source version, we have the LC main, which is the entry point. We have all the libraries that get loaded into the process, and then we have the debugging information, where the function starts, what data is in code, and we have the code signing information here. So now let's have a look at the most important load comments these days. And these are, for example, the definition of segments, load dilib, what libraries are we loading, DILT info only is the information where is the rebasing information and binding information and so on. And there's new stuff, that's the DILT change fix-ups. This is something that is for new information for fixing up pointers inside the binary, especially now with pointer authentication codes and so on. And there's that. Then we have the encryption info, which is basically the flag if this file is DRM protected or not. And then we have the code signature, which is basically storing where in the file is the code signing information. So let's have a look first at these segments. So for each segment we basically store what is the name of the segment, where in memory is it, how big is it in memory, and where is it in the file and how big is in the file, because a segment can be small inside the file but huge in memory, then it's basically filled with zeros at the end. We also need to store the information, what is the protection level of this segment. Is it a read-only segment, is it read-write, or is it just executable and stuff like that. Then each segment can be separated into sections, and we need to store how many there are, because directly after this segment comment header here we have a definition of each section. So the sections are not an own load comment, instead they are basically just added to the end of the LC segment 64. Each segment can also have specific segment flags, like this is an encrypted segment or not. So as I said, directly after the segment we have these sections, and so for each section we have this header here that specifies, okay, so what is the name of this section, where is it in memory, where is it in the file, what is the alignment, what kind of special attributes or flags do we have, is it a specific section type. So section types, which become clear in the next slide, is basically possible extra sections that contain information that is usually important for the dynamic linker. So there's a bunch of these defined in the source code, but two very important ones are, for example, the smod init func pointers and the sinterposing. So the smod init func pointers is basically the list of pointers that point to all the constructors of the code. So when you program something for macOS or iOS, you can specify constructors, but also destructors, inside your source code. And these are basically pieces of code that get executed before the main entry point gets executed. This is often used for security tools like dynamic libraries that you inject inside a process because they will be executed before the main entry point is executed. Yeah, as I already mentioned, there's also destructors, so there's also an smod term func pointers. Yeah, but that's basically it. Sinterposing is basically a triple of information. No, it's basically pairs of function pointers. So basically you have information like, oh, I want to replace a call to this function with a call to this function. So you can basically rewrite function calls on the fly by injecting a library that has interposing information. So you can say, for example, that all printfs go to a logging function instead and stuff like that. That can be also quite handy in security tools that you write yourself. So what types and attributes exist is basically defined in the header files that come with the SDK. Yeah. The next load comment we have a look at is the lc load dilib. This load comment is used for telling the dynamic linker that we need a specific dynamic library to work correctly to be able to import all our functions. And these are basically just stored as strings like the name of the library that we expect, but it also stores the timestamp that we expect on the library, the version number that we expect, and potentially a compatibility version, like this is the lowest version we can actually work with in case the one that we want is not there. Yeah, then the next thing is the dild info only. This is basically telling the dynamic linker where in the file is the rebasing information, where is the imported function, the binding information, the weak binding, the lazy binding, and where is the export tree for the exported functions. For this, there's also the dild_info command line util that allows you to dump this information basically to disk. New or relatively new is the lc_dild chained fixups. This one is stored as a link edit data command, so it basically just stores where is the data and how big it is, and then we have basically this kind of header for the chain fixup information, and then we have the tables and everything inside there. At the moment, let's postpone this information to another day maybe when we talk about pack. But basically the idea here is that this is a way to fix up pointers that is new or relatively new, and yeah, for example used for pointer authentication codes inside binaries. Now let's have a look at how dild info works. So we have the dild info tool and we can run it on bin. We can first see what it has. It has a bunch of command line parameters. So let's do something like dild info on bin ls. we can then see, okay, we have first of all x86-64 for macOS. We have all these segments and sections. We have the libraries that get unloaded. We have the same thing for ARM64, and that's basically that. We can then have more information about the fix-up, the export, the imports, and so on. But that's something we don't need to do right now. The next thing we want to look at is the encryption info 64. This one is basically just a marker that tells the system, oh, by the way, this file here is encrypted with some DRM. And then the loader can see that and basically use the right driver to apply DRM deprotection, and then the file can be actually executed with the decryption happening on the fly. The last one we want to look at here is the LC code signature. The idea here is basically that we specify where in the file is the binary blob that contains the signature of the file. So this again is stored as a link edit data comment with just specifying where is the data and how big is it. For the main binary, this is passed by the main kernel itself. For libraries and frameworks, the dynamic linker is responsible, and it will use a specific system called fcntl, f@add file6, to basically add the signatures of libraries to the running system. So how does this code signing information look like that we reference here? It's basically starting with a so-called super blob, and that registers a table of all the blobs that are inside the code signing information. And of course there's the command line tool code sign that allows you to dump the information that is stored inside the code signing information to disk. But in low level, this is how it's stored. So when you look at the blobs that exist, you can see that we have stuff like the code directory. We also have alternate code directories. So the purpose of this was that the code directory is signed by a certain algorithm, and maybe that is considered insecure in some short amount of time. Like for example, it used to use SHA-1. Then they added the possibility to have alternate code directories, so you could have the same code directory again signed with SHA-256 hash or SHA-512 hash and so on, to be more forward compatibility for the future. You have entitlements also inside these blobs. So this is basically an XML of what specific extra features does this file require, or what permissions. There's nowadays a dir entitlement, so it's dir encoded, so binary encoded entitlements. And the rest is going too deep here. So basically that's all the different kind of blobs that you can find inside a binary normally. Again, the code sign tool on the command line will basically dump all this information. Okay, let's have a look at how the code sign tool works. So we can use code sign dash d v to have a lot of information about this. So we use some app. We use the Pages app to see the code signing information of the Pages app. We can see there's a lot of information in here. So let's start. So we can see here we have the executable, we have the identifier, we have, what is this? Is it an
ARM64 or x86-64 Mach-O universal binary. We see information about the code directory, then the content of the code directory. We see the page table that is stored inside the code directory. We see the number of special slots is 7 here. So we have the hashes of -5 is the entitlements, -7 is the their entitlements. We have then the positive indexes in the hash table. Those are basically for each page in the file the hash. We can see they are SHA-256, and yeah, and in the very end we see who basically signed this, what was the team identifier, and so on. All of this comes from this here. We can also have a look at the entitlements. So let's use entitlements like this. Then it basically dumps out the entitlements of the file, so you can see what entitlements this pages binary has.